Fallbacks look fine in diagrams, but fail the first time a provider times out. I'll test LiteLLM Failover in Python with injected outages, so you know routing works before prod does it for real. This is the shape your solution will take when we finish, which simulates outages across providers and verifies the fallback route for a request. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. Real systems depend on several model providers. When one provider slows or dies, your app must keep serving users. LiteLLM helps by connecting to multiple providers and routing requests. But routing logic can hide in production until it breaks. Testing fallback behavior in a controlled way reduces outage surprises and avoids customer impact. Intuitively, fallback testing means forcing a primary provider to fail and verifying that a backup service handles the request. You want two things from a test. 1. The request actually reaches the backup when the primary fails. 2. The timing and frequency of failovers are visible, so you can tune timeouts and retry logic. This test mimics a small spike of failures, not a full chaos engineering exercise. We will build a small Python harness that injects failures, measures latency to recovery, and counts how often we switch to a backup. The code is intentionally tiny. It replaces the network call with a fake that sometimes raises an error. That lets us prove routing without touching real providers. Now we start the hands-on checks. Now we set up the simplest manual failover and show a single request moving to the backup when the primary fails. This snippet sets up LiteLLM and proves a simple manual fallback under a simulated outage. The variable client references the LiteLLM module so calls stay consistent across steps. The list M holds a minimal chat message we will reuse. The function fake completion stands in for LiteLLM's network call and intentionally raises an error when the model is primary bad, while returning a lightweight OpenAI-style dict for other models. By assigning fake completion to client.completion, we safely inject failure without touching any real provider. A try block calls the primary model, and on exception, the code invokes the backup model. The printed use model confirms the request was routed to the backup, validating the basic failover path. Next, we measure how long it takes to recover from a forced failure and complete a request on the backup. This example measures time to recovery by inserting a controlled delay before invoking LiteLLM's backup. The timer starts with time.perfCounter. Then client.completion tries the primary path that we previously set to fail fast. Inside the accept block, time.sleep imitates a provider timeout window, and the next client.completion goes to the backup model. After the call returns, the code computes milliseconds from the start time and stores it in latency_ms. Increasing the sleep duration simulates a longer timeout and will raise the measured latency. Decreasing it speeds recovery. The printed failover_latency_ms shows how long your system stalls before a successful fallback completes. Next, we run a small batch of calls to get a simple fallback frequency metric. This code runs a small batch to quantify how often LiteLLM falls back under controlled failures. The variable total sets the number of test calls. For the first 2 iterations, model is primary/bad, which our simulation makes fail. The third uses primary/good, which succeeds directly. Each attempt calls client.completion, and on exception, the code immediately sends the same message to the backup provider. The counter FB tracks how many requests required fallback, and rate divides that by total to produce a simple reliability metric. The printed fallback underscore rate shows that 2 of 3 calls needed the backup. A quick gauge of failover frequency. Now we try an integrated router construct so we can avoid manual try and accept in user code. This snippet uses LiteLLM router to perform a provider-aware fallback without custom try-accept logic. The router is created with a model list that maps logical names to provider models, including primary and backup. The call router .completion targets the logical primary and supplies fallbacks equals backup, instructing router to handle errors and reissue the request using the backup config. Internally, router delegates to LiteLLM's completion machinery, which in our test raises for the primary and succeeds for the backup. Changing the order or contents of fallbacks would alter the routing decision. The printed routed underscore model confirms router selected the backup after the simulated primary failure. Finally, we simulate a brief failure spike and produce a pass or fail style summary for resilience. This snippet produces an incident style summary that validates your LiteLLM fallback under a mixed failure spike. The loop runs 5 calls. The first 3 target primary/bad to force exceptions in our injected client.completion, while the last 2 hit primary/good and succeed. On each exception, the same message is sent to backup/good, simulating automated failover. The variable SB counts how many requests required the backup, and share computes the fraction of requests that failed over. Because we successfully route all failures to the backup, pass underscore rate is 1.00. The printed pass underscore rate and failover underscore share quantify resilience before real outages. In a real project, this pattern maps to health checks and can be run as part of a deployment test suite. You can run a short job that hits the primary and verifies both routing and timing without changing production traffic. That gives confidence that automatic failover will work when it matters. Recap. What it is: a small Python harness that injects failures into LiteLLM calls and validates fallback routing. When to use it: before deploying multi-provider routing or after changing timeouts and retry policies. One caveat: simulated failures can prove routing logic, but do not replace live traffic tests for latency under real network conditions. Next step: scale this exact test by adding timing and accuracy checks across a larger batch, and record the distribution of failover latency so you can choose a safe timeout threshold. If practical AI engineering helps, subscribe and watch the AI engineering videos.